Hello everyone, welcome to today's webinar. Today we will show you how to design and co-check diaphragm using IDEA StatiCa Detail. For this webinar, we are using the application GoToWebinar. So whenever you have a question to the webinar, feel free to type it into the question box on the right side, and we will try to answer all of your questions during the webinar or after it. And if we don't have enough time for all of the answers, we will send you by email. Let me introduce you to today's presenters. My name is Orsolya Kartali. I am product engineer at IDEA StatiCa. I have my colleague Petra Komarkova, also product engineer, here with me, and together we will show you how to solve this difficult problem of a diaphragm. Today's agenda will be the following. We will show you how to add effects of longitudinal prestress tendons, how to input the effects of transverse prestressing, and how to add shear stress flow from traffic loads. After that, I will show you how you should interpret your results. So now I ask my colleague Petra, please take the presenter and show our audience how to input the diaphragm.
Hello everyone. Can you see my screen?
Yes, we can.
So I will just make some modifications. So as Orsi said, we are going to show you how to model, design, and co-check diaphragm of a box girder bridge using IDEA StatiCa Detail. So let's get started. I launch IDEA StatiCa Detail, and I'm going to create a new project. So click on this button. Here we can specify the grade of concrete, so it's going to be C4555 reinforcement and concrete cover. Let's have 35 millimeters. I won't use any templates, and I will use this function general input because I would like to import the geometry from the DXF file. So we click on Import DXF. I will choose my prepared drawing. And by clicking on the edge and click on Consecutive and Outline, I will get the diaphragm into IDEA. And if we have an opening here, as we have, I just click on the opening and click on this button, and I have the geometry of the diaphragm. I can modify it. So the thickness of the diaphragm will be 1 meter. And I would like to have the opening a little bit lower. So let's shift it. So if I click on Real 3D Model, you can see the geometry of this diaphragm. We can notice that the structure cannot be calculated because it's statically overdeterminate. So we need to define supports. So click on Add New Entity, choose from the support. So in our case, it will be point bearing support. And let's modify the dimension of the bearing plate. It's going to be a little bit wider and thicker. And of course, we need to set the position. So let's have 1.75 meters. And this support can represent, for example, a pot bearing. I can copy this entity and create another support on the other side. So I would like to have a roller here, not a fixed support, and I just need to change the definition of the support, so it won't be from the beginning but from the end, and I have it here. In the next step, we are going to create some other entities. It will be bearing plate. This bearing plate will be used for application of prestress. I will show you later. So here we are just define the position. So, and of course the dimension. So the width is going to be 0.20 and the thickness will be 0.040 meters. The edge will be edge number 5, so we need to change this for number 5. And the position is all right. Then we need to have a second bearing plate, so we just simply copy this entity and change the edge. It's going to be edge number 3. It's here. So that would be all for the geometry. If I click on this 3D model, you can see the bearing plates and everything what we have defined here. In the next step, we will define the loads. Before that, I would like to say something about application of the load. Of course, we have group of permanent load. So the first step is define the self-weight of the diaphragm. So it's quite easy because it's based on the cross-section area of this member. So it will be line loads. So I will just rename this load case as a self-weight. Go to load impulses, and I'm going to add new entity. As I said, it's going to be line loads, and the intensity will be as follows. It will be minus 30.4 kilonewtons per meter. It's going to be acting on edge number 4, but it won't be on the whole length, but only on the part of this edge. And we just need to set the boundaries of this line load. And they will be 1.50 and 5.5 meters. This represents the mass of this part of the diaphragm. If I want to include these cantilevers, I will add another line load, but with the lower intensity, because we have less mass here. So I will change the intensity and change the boundaries by copying this entity and changing this function measured from end. I will get the distributed load on the other side. So that would be for the self-weight of the diaphragm. But we need to, we can't forget about the self-weight from the whole model. So if I go to global model, which looks like this, it was calculated in Midas table. We need to implement the reactions of the whole bridge. We know that we have some reactions here. If I go here, I can see the reactions. And somehow we need to transfer this load through the diaphragm to the bearing. So we will use this function that we can distribute the reactions along this length. So if we go back to our example and add more impulses, we're going to choose line loads, and we will set the intensity for 1403. The direction will be local x direction, and the position will be defined by 2 points. Sorry for that. Master point will be our diaphragm, or the master, and master point will be point number 4. And we know the geometry. For example, I can show you that we have some center line of the box girder bridge, of the box girder section. So we from AutoCAD we can define the coordinates of this line. So I know them, so I will just input them here. So it's going to be 1.76 minus 1.1. Of course, we need to define the second point. And the second coordinates are as follows. So by this, we are representing the transfer of the load through the web of the diaphragm to the bearing. If we copy this entity and we change the master points for point number 3, because it's this point, and change the x coordinates to minus, we can simply get this intensity. So that would be all for the self-weight. So we can go to load cases and combinations and create another load case. Yeah, okay, I would like to have the name here, so I just type it here. And the second load case is longitudinal prestress. Longitudinal prestress. So first, let me explain the application of longitudinal prestress. We know that these type of bridges are usually made of prestressed concrete, and we can have longitudinal and as well as transverse prestress. In this step, we are going to define longitudinal one, and as we know, primary effects of prestress or reactions from primary prestress are 0. So we are going to deal only with secondary effects. And we will apply forces from tendons directly into concrete by means of effective radius. So let me show you this in IDEA StatiCa Detail. So let's add new entity. It's going to be a point load. The value will be 61.2 kilonewtons. Direction will be global Z, and we set the inclination. It's going to be 9.50 degrees. Transmitting device will be none, because we said it's going to be directly into concrete. And we just set the effective radius. The effective radius is going to be 50 millimeters, and this value is equal to tendon duct. Also, we need to set the right position of the force. So let's choose the master point. It's going to be point number 4. And the coordinates are as follows: 1.76 and minus 1.60. You can notice that again it's based on some drawings. If I can show you, so we have these tendons, so you can simply read the coordinates from your drawing. So if I want to model another tendon, I just copy this, and only change is the change of the coordinates. So 1.81 and minus 0.89. And again, third tendon, 1.86 and minus 1.18. And the last one is 1.91 and minus 1.47. So that will be for the left part, left side, and I just need to do the same on the other side. So I copy this, and I will change first the inclination for minus. I change the master point. It's going to be point number 3, and of course the X position will be changed. And again, I will do this for all tendons. So it will just take some time for a while, but I think you can check easily if it's in the right way, how you wanted to model it or not. So it's quite easy. Copy and changing of master point and X direction. So we have the tendons, and now we can move on to another load case. Another load case will be also dead load, but it's going to be dead load of wearing surfaces and utilities. It will be applied in the similar way how the self-weight. So if I go to load impulses and add a new entity, I will choose line loads. So as you can see, the software can remind the last input. So I just need to change the intensity, and this line load distributed along the length is the same like in the self weight, but this is dead load. So that's why the only change is the intensity. By copying this entity and changing master point for point number 4, and of course changing of this coordinate, I can obtain another line load. So now we can add another load case, and this will be transverse prestress. So let's go to load impulses, and this will be very easy. You just need to add new entity. It's going to be point load, and I would like to explain it. So first, let's go to another slide, and this is how we are going to apply transfer prestress into our diaphragm. So we have 2 point forces. They are acting on bearing plates, and by means of this we are going to transfer prestress to the diaphragm. So let's change this value. It's going to be 1500. Direction is of course global X, and no inclination, and transmitting device will be bearing plate. I will do the same for the second side. I just need to change the value for minus 1500 and change transmitting device for plate number 2. So we have this load case, transfer prestress, and we are going to finish slowly, and this will be load cases which are including moving load. So let's name them as shear flow clockwise. So since we have unsymmetrical load due to moving load, we subject our diaphragm to torsion. So we have some torsion moment from the global analysis, and somehow we need to put our diaphragm into torsion. We will use this very known formula to calculate shear flow, and then we are going to apply this shear flow to our diaphragm by means of line load distributed along this curve. So I am in the load case shear flow clockwise, and I just need to add the entity. As I said, it's going to be line loads. The intensity is 300. And the definition of the position will be by polyline. If I click on this edit shape, I can define the coordinates of x and z and create the polyline. I have prepared this list of coordinates, so I just simply copy them and insert them into this table, and I can see the distribution of the shear flow along the cross section. So I click on OK, and I said it's going to be clockwise, so we just need to modify this value into -300. So this is the implementing of torsion moment. Of course, there are some reactions. We have tensile and compressed reaction, so we need to apply them as well. So I will just add new entity, again line load, but it's going to be defined by 2 points. And I just modify the value of the line load, and the points are already defined. It's again in the center line of box girder section. So this is the force on the left, and if I want to create the second force, second reaction, I copied the entity. I have to change the master point, and the x coordinates, and of course I need to change this value. So by this procedure we can apply a torsion to our diaphragm. If I go to load cases again and copy this load case, I'm going to rename it, and I just change the signs of this load case, and that's how I'm going to represent the torsion in other direction, and that would be anti-clockwise. So I'll just check if I did it correctly, and I'm afraid that I made the mistake here. So there should be, oh no, sorry, yeah, there should be 635, and on the other side there should be -37. And the shear flow will be +300. So now it is in correspondence. So we have defined all load cases, and now we need to define the combinations. So let's have several combinations. The first one will be ultimate limit state with the shear flow, so with the moving load clockwise. It's going to be ultimate limit state, and yeah, okay. So another combination will be for different shear flow from the opposite direction. And then we need to create serviceability limit state combinations. This combination will be characteristic. This will be also characteristic, but with anticlockwise shear flow. And if I add one more combination, this will be for quasi-permanent loads. So we don't need to distinguish between shear flow clockwise and anti-clockwise because there is no moving load in this combination. By clicking on this pen, I can change the combination rule. So let's have combination 610B from Eurocode. So for a self-weight, we need to calculate 1.15. The same will be for dead load, of course. Longitudinal and transverse prestress will be with factor 1, and shear flow clockwise will be 1.35 since we have here moving load, and the other load case will be equal to 0. This will be very similar to the first combination, but here we have this shear flow. Characteristic combinations will be with 111, and quasi-permanent will be without moving load. So if I click OK, I have created the combinations, and we can go on. The next step will be about reinforcement and some tools which can help you with designing of the reinforcement, but this will show you my colleague Orshi, because she's great at this explanation with topology optimization and liner analysis and so on. So Orshi, it's yours. So,
all right, thank you very much. So now I will share my screen. Can you see it?
yes.
Yeah, thank you. So topology optimization is a very useful tool that we have to design your reinforcement. Here I pre-calculated the topology optimization for several load cases and combinations. So you see the difference in the alignment of compressive struts and the ties that are created, the areas which are in tension. The red areas are the compressed ones, and the blue areas are the tensioned ones. So the first picture is, for example, for the dead load. The dead load is pushing down against the structure, so you see that these vertical struts are created, and at the top edge we have this tie, which is described in the blue color. The second example is quite opposite, is the effect of longitudinal prestressing. This prestressing, the secondary effects of it is pulling up the structure, so these vertical ties are created, and we have at the top edge the red compressed zone. Then we can make a comparison between shear flow clockwise and shear flow anti-clockwise. When you apply the torsion in the clockwise direction, you see that on the left side of the triangle, a tie is forming, and on the right side and at the bottom edge, we have the compression, the strut. Because quite opposite, the shear flow anti-clockwise on the right side we have the tie, and on the left side and next to the bottom edge we have the compressive strut. So we have to keep all these blue areas or these tension zones in mind when we want to design our reinforcement. So let's go right to it. First thing I want to reinforce is the bottom edge. I will do it by adding new group of bars, like that. I will choose the edge number 9 as this is the bottom edge. Number of layers, let's say we have 3 layers in the distance 200 millimeters. Their diameter will be 25 millimeters, and I want to have, for example, 5 bars in one layer. I would also like to change the anchorage type to standard hooks on both ends, and I would like to elongate these bars to the outer edge. You can do it by clicking here, whole length and extension, and choosing the extension up to the outer edge, just like that. Now I want to reinforce the top edge. Again, we add the new group of bars. We change the edge number to 4, and the number of layers, now I think 2 layers will be sufficient. The distance between them can be 100 millimeters. The diameter, I changed that to 20 millimeters, and number of bars in one layer should stay at 5. Anchorage, I will use the basic anchorage on both ends, and yes, that's it. Now I add some reinforcement around the opening. So by click new entity, we add the cage around opening. The diameter and the distances of the layers I will leave as they are by default, but I would like to change the anchorage type. We have now the perfect bond, which is a new, and it was a very requested feature. So this is how the anchorage looks like for the reinforcement around opening. Next thing I would like to do is add some wire fabric to reinforce the whole diaphragm. I can do this by adding a new entity and a new wire fabric. Let's change the diameter to 14 and 14 in both directions. Distances, we can leave it to 150 in both directions. And the number of fabrics should be 4. Now let's take a look at it in real 3D. This is how a properly reinforced diaphragm should look like. Really dense reinforcement. All right, we can move on now to check, and we can run the calculation by clicking on the top ribbon on the check. I have pre-calculated this example for you, so we can go right onto the interpretation of our results. So this is what we get out of the calculation. The first thing we see here is the summary of results. First, the ultimate limit state checks. We can see that the deciding combination was the shear flow clockwise combination. Here you see that 100% of permanent load and 100% of variable load was successfully applied on the structure before the calculation finished. And the deciding item was strength of reinforcement. Serviceability limit state checks. Again, we see that 100% of all the loads was applied. The deciding combination was the quasi-permanent combination, and the deciding item, it was the stress limitation. Here you can see more detailed result about that, and we see that the short-term result from the quasi-permanent combination was the deciding one, and for the crack width, the same combination, but for long-term results. Now we can move on to the more detailed check results. I'm sorry for the complication. Yes. So strength, first what we can see is the strength of concrete. Now we see it as percentages, which is the utilization of concrete. But we can change this interpretation to see the actual stress. You do it by clicking on the button in the top ribbon, and we see that here we have a concentration of compressive stress, which is 26.1 megapascals. The same applies for the reinforcement. Now we see the utilization in strain, but we can change that if you want to, for example, check out the stress in the group of bar or in the, for now, biofabric. This is the stress which is in the bars, or we can check out the strain of reinforcement. The next check is still ultimate limit state check, is the check for anchorage. Again, you can see all the detailed results for each and every group of bars. Then serviceability limit state, or first check, is the stress limitation check. Now we see the utilization of concrete for serviceability limit state for the quasi-permanent combination, and we can check out how much is it in megapascals. It's 18.4 megapascals for this combination. For the reinforcement, again, stress limitation check. In the top ribbon, you can change if you want to see the stress or if you want to see the utilization in percentages. The crack width results is our next check. Next check is steel serviceability limit state. Here our widest crack was 0.164 millimeters. In the top ribbon, you can change your limit crack width. We have by default set it for 0.3 millimeters, but of course you can change that if you want to have, let's say, a more strict criteria. We can check out the deflection, again, serviceability limit state check, and I will show you the deformed shape. You can see that the end of this cantilever was raised by 1.8 millimeters. This is the effect of transverse pre-stressing. Now we are finished with the results, and we can see how the bill of material looks like. This is how our tables of reinforcement look like. You can export that to DXF file and, let's say, open it in AutoCAD and further edit and put it into your drawings. You can change the scale, the units which you want to choose, and the layers into which you will export this DXF. The next thing I'll show you is the report. Now our report is generated. You can see on the left side that it is a fully editable report. You can check or uncheck the boxes that you want or don't want to have in your report if you want to have a more or less detailed report that you put into your project documentation. In the top ribbon, you can also notice that you can export the report into PDF document or doc document. If you export the report into doc document, all the results and all the text are fully editable. So if you want to change them, you definitely can. Creating the report takes quite some time because we have a quite difficult detail here. So in the meantime, I will ask Petra, do we have any questions from our audience?
Yes, we have some questions, but unfortunately we don't have much time. So I have chosen just two of them. So I don't know, can I read the question now, or do you agree? Okay. Yes. So the first question is it possible to use stiffness of the support and do not consider tension in support?
Yes, it is a very good question. So here we see the report that we can export, and now I will answer the first question. let's say if you want to insert support with calculated stiffness, you can do it in the geometry. If you add a new entity, which will be support, you have to choose the line support. Now I will demonstrate it. I will put a new support here to the edge number 9. And I don't want to have it on the whole length, but on the part of edge. Let's say the length will be 0.5 meters and the position 1.5 meters. And if I want to input the stiffness of this support, then I will click on this pen and input the calculated stiffness of the support. And here, by default, all the line supports are compression only. But if you want your support to act in both tension and compression, you can, of course, switch it off. And now the supports acts in tension and in compression too. What do you think, Petra? Was it the answer enough?
Yeah, I think so. So does it mean that if I want to apply the stiffness, I need to model line support, right? Not F1 support.
Exactly.
Okay, I think now it's clear. It's good to know. And the second interesting question was if it's possible to import reinforcement from DXF file.
Yes, again, a very good question. We can move on to the reinforcement. And here you can see that we have a button, import DXF. And if you, for example, pick one DXF file that you have prepared, and if I had my reinforcement already drawn here, I would pick the lines quite similar as Petra did when she input the geometry. I would click OK, and if I draw this reinforcement by polylines with a particular width, for example, 20 millimeters or 16, the model will automatically load the reinforcement in the corresponding diameter. So we will have groups of bars with 20 or 16 millimeter diameter bars. All right, so I think this is everything for today. And yes, we answered the questions. So I would like to remind you that after the webinar, we have a very short survey. Please fill out this survey. It only takes a couple of seconds. We will give you the recording in 3 days. You will find the recording on our website. And if you haven't tried IDEA StatiCa Detail yet and you are interested in it, you can get a trial version on our website also. Please don't forget to check out our resource center where we also have the recorded webinars. And our next webinar will be about IDEA StatiCa Steel, and it will be on the 28th of November. So thank you very much for your attention, and let's meet another time. Goodbye.
Thank you. Have a nice day.